Hi, I'm Gilles Pesant from Polytechnique Montréal. This teaser, entitled Combinatorial Search in CP-based Iterated Belief Propagation, describes joint work with Bilel Omrani, a master's student at Polytechnique, and Behrouz Babaki, formerly a postdoc at Polytechnique, now at HEC. So arguably the distinctive driving force of CP has been this direct access to problem structure that is exposed in its models from the use of high-level natural constraints. So that structure has been used to design efficient algorithms for domain filtering, to generate explanations, to branch during search, and more recently, to enrich the propagation mechanism at the heart of CP. What do I mean by this? So consider this simple constraint on two variables. Now in this grid, the dots represent the solutions. So you have each row representing a domain value for the first variable, each column representing a domain value for the second variable. And the green bars here are the domain values supported by this constraint, by the solutions. We could see this as projecting solutions onto each axis. Okay, but what if instead we could compute how many solutions support each domain value? For example, here in this second row, there are two dots, so 2 out of 16 solutions use that domain value for the first variable. That would correspond to computing marginal distributions on each variable. So our standard constraint propagation mechanism, where we basically exchange between constraints unsupported domain values, we could push further given those marginal distributions, which we could share between constraints, iteratively adjusting those marginal distributions until some stopping criteria. So in the end, we get for each variable a marginal distribution over its domain. Okay, how can we use this for search, to branch during search? This is the topic of this paper, where, among other things, we will tell you how we go from the red curve in the performance profile on the left to a much improved red curve on the right. Stay tuned. So I'll assume you've seen this teaser and know what the paper is about. We start by showing how to compute these marginals that we want to use to guide search. And we'll do this through a simple example of CSP on 4 variables, A, B, C, D, identical domains 1, 2, 3, 4, 3 constraints, and all different, a sum and a binary inequality. All domain values are supported here, so there would be no filtering. And then next, what happens? We basically apply belief propagation, so a message passing mechanism, here exchanging information between variables and constraints. Initially, there's no interesting message sent from variables to constraints, so let's look at what we compute to send a message from constraints to variables. In particular here, consider the blue constraint, and considering assigning value 3 to variable C. So we want to count the solutions to this constraint that would support that assignment. So there are 2. One where d is equal to 3, and the other one where d is equal to 4. So that's 2 solutions out of the 10 possible solutions to that constraint. And this is what we want to send back. So if we do this from every constraint, and considering all the variables in their scope and the values in the domains of the variables, we get all this information here compiled in a large table. That's received sent to variables. So for example, variable C here receives 3 messages from each of the 3 constraints. How is this combined? We simply take the product of the messages for each domain value. So you would multiply the values in each column and get the row shown in bold here at the bottom, which you can then normalize, and that would give you the marginal distribution for variable C. You do that for every variable, and then after one iteration, you get the marginals for each variable. Okay, we iterate again. This time, there's something interesting that the variables can send back to the constraint. In particular here, um, we'll be interested in what um, variable D can send back to the blue constraint, being the marginals shown here above from the black constraint. So again, for say value 3 for variable C, there are two solutions as before, but they don't have the same weight because the marginals from the black constraint tell us that value 3 for D is 3 times as likely as value 4. So we use these weights and sum them, and so we get a different contribution here that we can send back to the variables, different messages. And so that's how the marginals will evolve from one iteration to the next. Eventually, say after 10 iterations, this is the picture of the marginals for all the variables. We see that there's a pattern emerging here. We see that it's suggesting that value 1 should be given to variables C and D. And for variables A and B, it's sort of half and half between values 2 and 3. That's actually quite close to the true marginals that we can obtain by just looking at the solutions to the whole problem. There are actually two solutions, 2311 and 3211.
So now that we know how to estimate these marginal probabilities, let's discuss how we can utilize this new information to guide search more efficiently. So in this work, we investigate this question, and we designed four variable value ordering heuristics that leverage this additional information provided by the CP/BP framework. So I'm going to illustrate these four heuristics using the following simple problem. I have two variables, x and y, with their domain over here. And let's suppose that we estimated the marginal probabilities using the previously described procedure. So the first heuristic is max-marginal. The idea is very simple. We branch in the direction that maximizes the marginal probability. So in this case, this would be y equals 2. And upon backtracking, we obviously disallow this value. The second is min-marginal. So here the idea is to look at the variable value assignment that minimizes the marginal probability. And on the left branch, we disallow this value. Then we have max strength. So here the idea is to compute a sort of divergence measure between the marginal probability and the uniform distribution, which is just the reciprocal of the domain size. And max strength branches in the direction that maximizes the positive difference between the marginal and the uniform distribution. And finally, min strength, similar ideas, except that on the left branch we disallow the variable value that minimizes this marginal strength. So we now present initial results on the application of the CP/BP framework for solving CSPs. We compared the four heuristics based on a wide set of benchmark problems taken from the XCSP lib, and we investigated two search algorithms: depth-first search in full lines and limited discrepancy search in dashed lines. So we were interested in comparing the different heuristics based on how well do they guide search, so we plotted the percentage of solved instances versus the number of failures. So overall, we observed that LDS is performing better than DFS, which is something expected when the heuristics are well informed. We observed that in some problems we're not doing that well. For instance, on car sequencing or Dubois, we're solving the best heuristic is solving 40%. So we will have the opportunity to come back to these problems later on because they exhibit interesting features. And out of the four heuristics, we observed that max-marginal is performing slightly better overall. So here are additional results. So again, very similar conclusions over here. So our intermediate conclusion is that max-marginal with LDS is a good candidate for a general-purpose branching algorithm. And compared with the initial work that introduced the CP/BP framework, our recommendation, the conclusion here is slightly different. The initial recommendation was to use max strength with DFS, but it was based on a smaller benchmark. So here we benchmarked on a wider set of problems, and our conclusion is slightly different. So we want to investigate max marginal with LDS as a good candidate. So because we're using LDS, we can use the number of discrepancies as a proxy for how well does the heuristic is guiding the search. So here we are interested in max marginal. We represent the percentage of solved instances per problem colored by the number of discrepancies introduced in the search. And interestingly, we observed that in some problems, for instance, primes or Latin square, we solve a large proportion of them, a large proportion of them in very few instances, very few discrepancies. Sorry. So this indicates that max marginal efficiently searches the solution space. So then we compared max marginal against the default search in the best CP solvers of in the latest XCSP competition, Choco and Abscon. And as a baseline, we also introduced mean domain with rounded value ordering. So again, we plot the percentage of solved instances versus the number of failures. And here we see that we perform better than state-of-the-art on Latin square, magic square, and multi-knapsack. But we perform worse on Dubois and Kakuru. Again, additional results with very similar trends. We beat state-of-the-art on primes, nonogram, and partially filled magic square, but we perform worse on Pigeon Plus.
Our initial results show that CPBP does not perform very well on certain instances, in particular Dubois and Pigeons Plus. This motivated us to take a closer look at these instances. Let's start with Dubois. These instances are defined over n binary variables and consist of 2 times n ternary constraints. One of these constraints says that a certain triplet of variables should have an even number of ones. Other constraints say that other triplets should have an odd number of ones. These instances are constructed in a way that makes them unsatisfiable and have proved to be challenging for different search heuristics. As you can see in this plot, which has a logarithmic x-axis, all different solvers and search heuristics show an exponential behavior. They effectively have to enumerate all potential solutions. In particular, CPBP has the problem that the marginals are uniform at the beginning of the search, and even after the branching they stay uniform. So CPBP doesn't have much information to guide the search. On top of that, CPBP uses LDS, which makes it likely to visit nodes multiple times, which explain this gap in failures. Interestingly, there's an extension of CPBP which can potentially solve these instances trivially. The key is to maintain marginals over subsets of variables instead of single variables. If you're interested, there's a short discussion in section 4.1 of the paper which explains this further. A similar situation is going on with Pigeons Plus instances. Again, the instances are unsatisfiable, so a complete exploration of the search tree is required. Once again, the marginals are uniform and remain uniform even after branching, which leaves CPBP with not much information to guide the search. In such cases, it's probably best to fall back to another search heuristic. Luckily, such cases are easy to identify early on during the search. Now let's have a look at another phenomenon that can hurt the performance of CPBP, namely marginal oscillation. When the constraint graph contains cycles, there's no theoretical guarantee for the convergence of belief propagation. So it's possible that in consecutive iterations the beliefs do not converge to a value, or in this case even diverge from the true marginal, which is shown by this dashed line here. There's a known remedy for this phenomenon, which is known as message damping and involves tweaking the message update formula. Here, when calculating the variable to constraint messages, we take the average of the incoming messages and the old beliefs. The parameter lambda is called damping factor and determines the trade-off between the new message and the old belief. In this plot, you can see that we have tried message damping with 3 values for lambda. And even though all of them eventually cancel oscillation, for this particular instances, the value 0.25 seems to lead to faster and smoother convergence.
So now we present our final comparison. We benchmark the heuristic without damping, that's lambda equals 1 over here, with 2 variants, lambda equals 0.5 and lambda equals 0.25, to benchmark the message damping. What we see is that on problems where we already perform well, like Latin square, it does not hurt performances to add message damping. On some problems, it even helps a little bit, like multi-knapsack. But more importantly, on car sequencing, it helps significantly improving the performance. And car sequencing was the original motivation for looking into message damping. Additional results over here, again, very similar trends. Now, in terms of running time, we wanted to compare against state-of-the-art also in terms of running time, even though the comparison is not strictly speaking ideal because the solver that we're using is not as optimized as state-of-the-art. So it's more difficult to isolate the effect of the branching heuristic, but still it gives an idea of what kind of improvements can be expected out of the method. So obviously the iterative belief propagation operation, it's a rather costly operation, so it does not help systematically in terms of running time, but the additional guidance that it provides often helps us remaining competitive with state-of-the-art. Those are, again, additional results with very similar trends. So yeah, in terms of running time, we identified several directions where we can improve because we saw that in terms of guidance, belief propagation provides very rich additional result that can be exploited, and we identified several directions in which we can improve running time. So now I'm going to conclude our talk. So in this work, we investigated the use of search heuristics for the CP-BP framework using a wide set of benchmark problems. And from this empirical study, we propose max-marginal with LDS and message dumping as a generic branching algorithm to guide the search. So it was shown to successfully guide the search while often remaining competitive with state-of-the-art in practice. We identified several directions for improvements for future works. So first, we identified cases where marginals are not worth computing, as it is the case when they are uniform, for instance. So it would be interesting to take advantage of this simple identification to stop wasting compute efforts and switch to something else that could improve the running time in these cases. We also identified a large number of quasi-ties instances for when branching, so it would be interesting to see what can be done in these cases. Should we proceed differently? And how can we improve branching in these conditions? And finally, in all of the experiments that we presented, the number of BP iteration was set to 5. It would be also interesting to tweak this hyperparameter online depending on the quality of the estimates. And this can also help reducing the running time. So this concludes our talk. And with that, thank you very much for your attention.